All right, everybody. Today we're going to look at graphing the other trig functions. So we've done sine and cosine. So now today's our day to do tangent, cotangent, and secant and cosecant. So we're going to get right into this here to do the parent graphs. Tangent and cotangent graphs have four intervals, which we're going to graph over, just like sine and cosine. But to make it a little bit more user-friendly for us, for tangent, I'm going to do two intervals to the right and two to the left. And I'm actually going to go by pi over 4. So I'm going to be using an interval of pi over 4. You'll see why in just a moment. And then so one unit to the left would be negative pi over 4, negative pi over 2. So we need to remember some unit circle values here to be able to graph tangent. So let's think about what those might be. Tangent at 0. So use your pink sheet if you need to, if you can't remember off the top of your head, but these are just special value unit circle numbers, so hopefully you do. Tangent of 0 is 0. Tangent at pi over 4 or 45 is 1. And then tangent at pi over 2, 90 degrees, is undefined. Remember, tangents like slopes, so at vertical it'd be undefined. So undefined places on the graph we either show with open circles if they're removable, or vertical asymptotes if they're not. Well, this is definitely not going to be removable. There's no fraction there to get rid of it. So we have actually a vertical asymptote at pi over 2. Okay, that was totally not straight at the bottom. There we go. All right, so going in the negative direction, and we'll talk about why we're going in the negative direction in a second. Negative pi over 2 would be negative 45 degrees, or quadrant 4. So tangent would be negative 1. So 45 is a reference angle, would be a 1, and then it's in quadrant 4, so negative. Negative pi over 2, that's like negative 90 or 270, if you want to think of it that way, also undefined. All right, now the best way I can describe the shape of this is it's sort of like an x cubed. So imagine what an x cubed looks like, but it's bounded by these asymptotes where x cubed isn't. So the graph looks something like this. Okay, and arrows on the end, it continues to grow and approach those asymptotes. Now, I want to show you what one more looks like so we can talk about how this cycles. So let's add 4 more intervals going to the right here. You could do 4 to the left as well, just easier to do the tick marks. This third interval then, think about what that would be. If 1's pi over 4, that would be 3 pi over 4, 4 pi over 4, or pi, and then 5 pi over 4, and then 6 pi over 4, or 3 pi over 2. Let's do a few more values so you can see what this graph does as it continues. So 3 pi over 4, tangent, that's 135, which is quadrant 2, so negative 1. Tangent of pi is 0. Tangent of 5 pi over 4. 5 pi over 4 is 225, or quadrant 3. Tangent's positive, because both x and y are negative. And then 3 pi over 2, 270, we are undefined again. All right, so we get our curve. Again, kind of like an x cubed, but it's bounded by these asymptotes. So this graph, this pattern, just continues infinitely in both directions. So if you have a highlighter, why don't you go ahead and highlight one complete parent graph for tangent. Starts at negative 90, goes to positive 90. The reason we pick that one is it's kind of, I don't know, most people like to have a complete graph that they're looking at in some sense, so I guess it just depends on how people choose to do this, but this is the one most people pick, as opposed to starting at 0 and getting half of a tangent curve and then another half. So I know it looks a little bit goofy. The length of the graph goes from negative pi over 2 then to pi over 2, or negative 90 to 90. So the length of the period of one complete graph is only pi, or 180. So it's actually shorter than what sine and cosine parent graphs are. It repeats more frequently. So the period function formula would be pi divided by k only. So whereas before we had 2 pi divided by k for sine and cosine, this would only be pi divided by k. Another thing to talk about, let's talk about amplitude. Technically, definition of amplitude is a distance, right? The distance from the middle to the top or the middle to the bottom. But there is no top, there is no bottom. So technically, we can't really talk about amplitude. There's no height of these curves or these waves. However, if you put a number out front, like if we put a 3 out front there, it would still vertically stretch the graph. Those points that are 1 and negative 1 would go to 3 and negative 3. So it's still stretching and compressing, but it's not going to have a top or a bottom. So you can still stretch and compress. That still happens, but we can't technically name it an amplitude. So when you're thinking about what types of things we're talking about, we can't really have an amplitude for that. All right, let's do cotangent. So same kind of thing. We're going to use 4 intervals, but for this parent graph, we can actually just go to the right, and we're going to still go by pi over 4. So you'll see why in just a second. And then we're going to go ahead and graph these on our graphing calculator after we're done graphing them by hand, so you can see what that looks like too. So how do you find a cotangent graph? Well, cotangent is just the reciprocal for what tangent is. So I'm going to have you referring back to your old graph, and we're just going to flip those values. So tangent at 0 was 0. So if you flip it, Zero's reciprocal is undefined. So this graph actually starts with an undefined place. Pi over 4 tangent's 1, so its reciprocal would still be 1. Tangent of pi over 2, that's undefined. So the reciprocal, cotangent, would be 0. 3 pi over 4, it was -1. Reciprocal would be -1. And then pi. Tangent of pi was 0, so cotangent would be undefined. So this graph actually starts and stops also one complete period with an undefined place. And if you think about the shape of the graph, the thing it looks most like to me is like an x cubed that's flipped, reflected over the x, but again, it's bounded by these asymptotes. So it's not exactly x cubed, obviously, but it has that sort of feel. All right, let's do one more so you can see what's happening. So we'll do one more set of 4 tick marks. Let's label the axes here. So 5 pi over 4, 6 pi over 4, so that reduces, 7 pi over 4, 8 pi over 4 would be pi over 2. So see if you can follow the pattern. We'll just keep going. So tangent at 5 pi over 4. I know we didn't do that on our old graph, but 5 pi over 4 tangent, that would be quadrant 3. So tangent is +1, so this one would be +1 as well. See if you can follow the pattern. What should happen next is it should go from +1 down to 0. See if that makes sense. 3 pi over 2, 270. Tangent is undefined, so cotangent would be 0. 7 pi over 4, that's quadrant 4. Tangent is -1, so cotangent would be -1. And then 2 pi all the way around, tangent is 0, so cotangent would be undefined, and we get another one. And it keeps going infinitely in both directions, keeps going and going and going. So we have this idea of our parent graph then. Before it repeats itself, the easiest one for people usually to pick is the one that goes from 0 up to pi, or 180 degrees. So the period, the length of this graph, again, is pi, or 180. So it's half as long as what sine or cosine was. So the period formula then would be pi over k. And again, for amplitude, we have to say none, but you still can have a stretch or compression. So there still can be a stretch or a compression depending on what that number out front is. If it's a 1, it's the regular graph, but it can still stretch or compress depending on if that value changes. So it's really easy to figure out cotangent if you know what tangent is. All right, so let's take a quick peek at the graphing calculator so we can see what that looks like. I'm going to have you go ahead since I'm going to go back, I guess, so you can have it right next to it. So let's look at the tangent one. We'll graph it on the calculator quick. So y equals tangent of x. Please make sure you're in radian mode on your calculator. And I'm going to do just the regular window, -10 to 10. So the fastest way to get that is zoom 6, and we can see what the graph looks like. Because what I want you to see really is how many of these there are. It continues infinitely in both directions. So we just had the one parent graph that we talked about. So the one that we highlighted, that was this one. That's the one that starts at -pi over 2, goes to pi over 2. If our scale is -10 to 10 radians, once around the circle is 6 or 2 pi, so like 6.28, so 10 radians, it's almost twice around the circle. So you're going to get a whole bunch of these graphs because in every unit circle, if it takes only pi, there's 2 of them. So if we have like almost 2 complete times around, we're going to end up with a lot of graphs here. So it's going to keep continuing infinitely in both directions. So I kind of want you to see what that looks like. The next graph, when you do cotangent, let's talk about how you type that one in. We don't have a cotangent button on our calculator. There isn't one. So how do we type in cotangent? Well, it's the reciprocal of tangent, so 1 divided by tangent of x. And let's see what that one looks like. So we get that repeating graph over and over again, -pi or 10 radians to +10 radians. We get a whole bunch of repeats on this graph, but here's the one that we talked about, the one that goes from 0 to pi, and that's the parent graph that we use that we can move around. So all those different things we can do to these graphs, shift them up and down, left and right, whatever, all the numbers do exactly the same thing in the graphs that we expect them to. So we'll look at that in just a sec. Okay, let's talk about sine and its reciprocal now. So I want you just really quick, you want to graph one complete period of the regular sine graph, which is something that we've studied pretty extensively. So just the regular sine graph, I think sometimes it's easier to look at that graph first. So we start at the middle, max, middle, min, middle, and we have our curve. Okay, now I want you to set up the exact same scale to do the cosecant graph. So we're going to think about what this picture looks like. And it's going to have the same period as the original function because it's just reciprocal, so it's going to always have the same period. And I want to think about what each of these values do. So we're going to go point by point on the graph of sine and find the reciprocal to be able to graph cosecant. So at 0, sine is 0. So the reciprocal of 0 is undefined. So you're going to have undefined places on this graph. So where else would cosecant be undefined? Well, it's going to be every other location where sine is 0, which happens at pi. Oop, kind of missed the tick mark there, and 2 pi. So when you're thinking about what happens on cosecant, anywhere sine is 0, cosecant will be undefined. All right, let's talk about the other places. At pi over 2, sine is 1. Well, the reciprocal of 1 is still 1. At 3 pi over 2, it was negative 1. So at 3 pi over 2, it's still going to be negative 1. That's the reciprocal. But what happens in between there? Okay, so I'm going to do one more value for you so we can see what's happening, or a couple more. Sine of pi over 6. Pi over 6, remember 180 divided by 630 degrees. What is sine of 30 or pi over 6? So that would be a half. So that's a special value that most people are pretty comfortable with. I'm putting it in on the original graph. So 30 degrees or pi over 6 would be a half. What would be cosecant of 30 degrees then? Well, reciprocal of a half would be 2. So at 30 degrees, this graph is going to have to be up at about 2. That gives us another point to kind of think about. Let's do one more on the original. So sine then of 150 would also be a half. Right, so 5 pi over 6 or 150. So at 150, we're also going to be then, for cosecant, at 2, because the reciprocal of a half is 2. So the best polynomial sort of guesstimate of what this graph looks like is a parabola opening up. So think of it sort of like the vertex at 1, and then the parabola opens up. So that's, or parabola-like shape, it's not a parabola. So there's those vertical asymptotes to contend with. So what's going to happen between pi and 2 pi? Well, you can do the same thing here. You could do your negative 1/2 at 7 pi over 6. Well, that means it's going to be a negative 2 at 7 pi over 6 for the reciprocal. Same thing here in quadrant 4, we'd have a negative 1/2. So we're going to have a negative 2. So what you get is that same sort of parabolic shape, but opening down. And this is the graph that repeats itself. So the next graph, if you go to 2 pi to 5 pi over 2, you'd have one opening up, and then there'd be another one opening down and another one opening up, and it continues infinitely in both directions. So let's go ahead. I'm not going to make you draw another one here for time purposes, but let's go ahead and highlight the parent graph. So it's one opening up and one opening down. So the period of this graph, the length of it is 2 pi, same as the original function. So our period formula would be 2 pi divided by k. And again, amplitude, is there a top or a bottom? Absolutely not, there isn't, but you can still stretch or compress. That still happens, so that's totally fine. But it's just not going to technically have an amplitude number because there's no height that we can measure. Now, here's one way that people like to look at this, and this is kind of a cool way to think of it. I'm going to go ahead and graph in here for you the graph for sine. Okay, so I put in the graph for sine, the green one. Some people like to overlay sine and cosecant together to see what that graph looks like. So if you want to graph cosecant, you could just put the graph for sine in there first, and then just go through each of those locations and do the reciprocal. So everywhere that you see these zeros, those are going to have to be where your asymptotes are. The ones and negative ones stay put, and then all the points that are between 0 and 1 have to be reciprocal, so they're going to be bigger than 1, and same thing down there. So some people really like that overlay idea to see the connection between the two graphs. So if that helps you, go ahead and graph sine first, and then you can do the reciprocal. All right, so let's take a look at cosine and do exactly the same thing. So go ahead and get yourself one complete graph for cosine. So we'll get that graphed. So 1 and negative 1. So cosine starts at its max, middle, min, middle, max. All right, so we're going to set up the scale for the reciprocal exactly the same. So we have the same period for both of these functions. All right, we're going to do the same thing we did last time then. We're going to take every point on cosine and do the reciprocal. So reciprocal of 1 would be 1. At pi over 2, it was 0, so that means it's going to be undefined. Where else would this graph be undefined then? Where else is cosine 0? 3 pi over 2, so it's going to be undefined there as well. At pi, it was negative 1, so it's still going to be negative 1. Reciprocal of negative 1 is still negative 1. And at 2 pi, still 1. Okay, now I have to figure out what this graph is going to look like. Remember, sine and cosine are pretty much the same graph. They're just shifted off 90 degrees from one another. So guess what? Secant and cosecant are basically the same graph, just shifted off 90 degrees from one another. So let's see if we can see what that picture would look like. So I'll get another point in here. Let's do cosine of 60, or pi over 3. So cosine of 60 is the half. So that means secant of 60 would be the reciprocal of a half, which would be 2. So that'd be somewhere up there. So you have this half a parabola opening up. I know that looks a little bit goofy. If you went back to negative 90, you would get the other half of the graph over there. So it would be coming up over here. You get that other piece of it. At between pi over 2 and 3 pi over 2, you'd have the ones that would be at negative 1/2. So they would be at negative 2. So you have your parabola opening down. And then between 3 pi over 2 and 2 pi, you would have your positive 1/2 again, which when you do the reciprocal would be positive 2, which again, it's kind of goofy. You only get the half, but if you kept going to 5 pi over 2, you get that other half of the graph. So you would keep going, then you'd have another one opening up and another one opening down. So this parent graph looks a little bit goofy to people, but if you want to keep it the same from 0 to 2 pi, like your cosine graph, you really get half a parabola shape, the one opening down, and then the other half opening up. So the period, once again, is 2 pi. So the period formula would be 2 pi over k. And once again, amplitude, you really got to say none because there's no top or bottom, but you can still stretch or compress. And we will see that when we do some of our sample graphs here in just a second. So once again, what people like to do is they'll put in the cosine graph first to see what the shape is, and then they take each of those values and do the reciprocal. So reciprocal of 1 stays put. Reciprocal of 0, that becomes the asymptote. Negative 1 stays put. 3 pi over 2, it's 0, that would be the asymptote, and then back to 1. So it's a really nice visual for being able to see what that parent graph looks like. Okay, so what do all the numbers do? In the equations that we talk about then, we still should be able to identify, like what we did for sine and cosine, our list of information and be able to make a sketch. We're really not going to emphasize this part of the graphing quite as much, but I still want you to be able to identify what would happen, and we'll stick to things that are a little bit easier. All right, so I want you to see if you can identify what is the a value in this equation. So just be careful. The a value is the 1. Now, a lot of people look at that and the first number they see is a 2, so they want a to be 2. But remember, you could have written this one like this. So secant of theta plus 2. What is the 2 actually representing? That's your vertical shift. So this graph is moving up 2. A is 1. What that tells me is there's no stretch or compression. There's nothing that's been stretched or compressed vertically. So no stretch or compression vertically. But when you answer the question, you really need to say amplitude is none. There's no top and no bottom, so you can't measure a height, but there's also no stretching and compressing. So the graph is going to be the same vertical stretch or vertical shape that it was normally. Period. What's k? Well, k is found in the same location it always is. It's the coefficient of the angle. So in this case, k is 1. So that means our period is 2 pi divided by 1. How do I know it's 2 pi divided by 1? It's secant. That's the reciprocal of cosine. They have the same starting period. So 2 pi divided by 1, it's 2 pi. What that tells me is it hasn't been stretched out horizontally at all. It's the same length. Phase shift. Do you have one? Absolutely not. So there isn't one because there's no parentheses. We haven't moved left or right. Is it reflected? Nope. Not reflected because the a value, that 1, is not negative. So when I say a, I'm thinking about like the number that is in that slot, but remember there's technically no amplitude. All right, so let's go ahead and set up our scale. It's the same as what we were doing before. You always want your period to be that last tick mark. So we'll have that in there. Gonna have to have a little bit of room to maneuver here, so I'll give myself a little bit of space on the vertical axis. Okay, so where's your new middle of the graph? Good thing to think about kind of at the get-go here. The new middle of the graph is at 2. So I'm going to go ahead and put in my midline. It's a much easier way to think of this. If you slide a graph up or down, will it affect the locations of your asymptotes? Well, not at all, because if you move up or down, there's still those vertical lines. If you move left or right, well then yes, we definitely have to deal with that. So phase shift will affect the locations of the asymptotes, but vertical shift will not. So think about secant. Wherever cosine is 0, secant is undefined. So our vertical asymptotes are going to be occurring at pi over 2 and 3 pi over 2. All right. Now, the places where secant was 1, so at 0 and 2 pi, those have to move up 2. So this whole graph is moving up 2. So what was at 1, up 2 from there would now be at 3. Now, some people like to do it like that, just slide the points up. The other way to think of it is look at where those points are. They're 1 above and below the middle. That's where those, like if you want to call them vertices, I guess, those points where those curves start and stop, they're at 1 and -1. So they're 1 above and 1 below x equals, or the x-axis normally. So if we move the graph up 2, that's the new middle, so it's going to be 1 above that. So it's another way to think of it. And you'll have your half curve opening up. Okay, then the one that was at -1, so the original parent graph would have been pi -1. If you move that up 2, that means it'll be at -1. Now, another way to think of it again, that's 1 below the new middle of the graph. So we're maintaining that. We haven't stretched it or compressed it at all. So you have 1 opening down. All right, then at 2 pi, normally that would have been the 1, but now up 2, that would be at 3 or 1 above, and we have our other half there, so we can see what that picture would look like. So kind of cool just to think about some different ways you can think about what that graph would look like. I'm going to go ahead and put something in here for you so you can see this. What I just graphed in green is the cosine plus 2. Right? So cosine graph slid up 2. Some people graph that first. So they graph the cosine function with a vertical shift of 2, and then they just do the reciprocal. So you're starting with the cosine graph and then thinking, okay, what happens to that? Well, that's where it's going to start, and then the undefined places stay the same, and we have our graph. So if that's easier for you to think about, it's a great way to visually think about what that looks like. Okay, our last one here, so we can get this sorted out. So we have amplitude. That technical answer is none, but we have a vertical stretch of 3 times as tall, because the 3 out front. The period is 2 pi divided by k. Well, k is 1, so it's 2 pi again. Phase shift is 0. Vertical shift is 0. We don't have any add or subtract at the end, and it's not reflected, so that's a no. So I'm not going to give you a lot of things that you're going to have to worry about in terms of stretching and compressing. We're just really only going to be focused on maybe one thing, because these get kind of crazy anyway. All right, so set up your horizontal scale to whatever your period is. And then we have a vertical stretch of 3. So I want you to think about what that would do for a sine or cosine graph. If you times it by 3, that means your max and min points would move up to 3. It's going to have the same effect, because when you do the reciprocal of a 1, still a 1. When you times it by 3, it's still going to be a 3. All right, so let's talk about cosecant. Where is cosecant undefined? Well, that's where is sine 0. So that's at 0 and pi, and then 2 pi. All right, now think about what you get at pi over 2. Normally, sine of pi over 2 is 1, so cosecant of pi over 2 is still 1, but then when you times it by 3, that means that vertex idea of where that first curve is going to be up at 3. At 3 pi over 2 is normally -1, but now you times it by 3, so now it's going to be down at -3. And there's your vertical stretch. Those two curves are pulled further apart than what they were before, so we have that vertical stretch. I'm going to go ahead and put something in here for you then. Look at my red graph. That's a graph of 3 sine of x, which is the reciprocal. So if you want to graph 3 cosecant, you could graph what I just did in red first, and then do that reciprocal idea. So it's a kind of a nice way to be able to see both of those pictures. So just to kind of finish up today, I want to show you on your graphing calculator really quick. If you want to graph either secant or cosecant, if you forget what the picture looks like, remember you have to do 1 divided by. So I'll do just cosecant, so 1 divided by sine, just so you can see the parent graph. Obviously we did times 3 in this picture, but at least you'll get to see the shape. If you go -10 to 10, you will see all of those curves going up and down, which is a really nice way to be able to look at that. So there's our original graph. Now I'm going to go ahead and graph the 3. So it would be 1 divided by, I'll make sure we get this whole thing in the bottom, 3 sine of x, parenthesis, parenthesis, and then what you're going to see is that next set, oh, I have a 1/3. Sorry, I typed it in there wrong. I have to get the 3 on the top to make that. Sorry about that. Typed the wrong one in there. So let's go ahead and, I was supposed to put the 3 on the top, not the bottom. So 3 divided by sine of x. There we go. So reciprocal and then times 3. I did a 1/3, so it made it flatter. Not the one I wanted to do. So there we go. There's our 3 cosecant, or 3 divided by sine of x, so stretching it apart 3. All right, so when you think about these reciprocal graphs, think about the original first, and then you can do the reciprocal a lot easier. So this kind of part 1 will be all the graphs and the equations that have to do with that.